My name is Craig Box. I work on the Google Developer Relations team looking after our container service products, Kubernetes and Istio. I'm here today to tell you a little bit about managing microservices with these platforms. Please do feel free to contact me on Twitter. Otherwise, I'll be happy to take questions at the end and also be in the discussion area outside afterwards. Today, I'm going to introduce to you a new concept which has come about this year called a service mesh. Talk a little bit about how we got to needing one, the architecture of the Istio service mesh, and then obviously any questions. So at a high level, we think about the network as a pipe that just moves bits around. But we don't really want to worry about bits or MAC addresses in our applications. We want to worry about services and the connections that they need to make between them. So if you think about that from a OSI perspective, we have a layer 3 network, whereas we want to think in terms of layer 7. So what would it look like to have a true layer 7 network? We might want to do things like route traffic around services that have failed, where you can connect to the service, so layer 3 is up, but the service isn't doing what it wants to do, to improve the reliability of your applications. We should be able to get insight into what's happening in our cluster, find unexpected dependencies, find out root causes of failure. We should be able to avoid unnecessary overheads, like high latency connections, or servers that have a cold cache and haven't warmed up yet. We want to be able to make sure that traffic between services is secure against trivial attack. So we want to have mutual TLS authentication without having to build that infrastructure into every application that we write. And then we want to be able to impose policy on what we do with our applications, not just at the connection level, but thinking higher level at the applications. So a service mesh is a fabric that lets us provide for these concerns in a microservices environment. Now, to think about why we need to solve these problems, we think back to the way we all used to do software development. It was reasonable to describe your problems with a monolith. You might have an application that looks a little bit like this. So all of the code is there. Why not use it? Why not connect between places? Why not have strange dependencies that wrap back on each other? Then if we want to redeploy this application, we have to redeploy every module even though things haven't changed. We have to have the application all written in the same language or in compatible languages, even if we have diverse teams working on them. It's difficult to test this as well. These are individual parts, but we can't exercise them independently. So ultimately, we wanted to solve all of these issues, so came along microservices. So we have decomposed the monolith. You'll notice that in this example, we've removed some of the crazy dependencies. We've stopped using internal methods called from other modules. And we've created these services out of the modules that we used to have by creating abstractions. In the cases where we need to store state, for example, each service should have an independent state so that your connections to it can succeed or fail depending on, without worrying, about what's happening in the rest of our environment. So this is fantastic. We've gone from a world where we have these giant complicated applications to something that's new and looks really good on your CV. We've gained development velocity. We've stopped using these internal methods. We've created these services. We can scale them independently. We can say this service now needs to be bigger without having to scale everything else that goes along with it. We can test because of the abstractions that we have created. But what have we lost? What was the cost of this? We had reliable calls inside our applications because you were just calling a function or a module. We've now replaced that with an unreliable remote procedure call. It may not always succeed. The service on the other end may not always be available. We were secure. We were running inside the same process and then inside the same machine. Now we're connecting to services which might be on different machines on an untrusted network. Previously, access control could be assumed because you knew you were both ends of the connection inside your monolith. Now, there may be other people on this network who are trying to connect to services that they shouldn't connect to. our latency latency has gone up, and our ability to measure why our latency has gone up has gone down. We are now having these stepped connections throughout the services that make up a single module call. And we can no longer just step through the application in a debugger and find out what's causing that. And, well, that's a problem that we may not know how to solve. We need a complete new set of tools, all to get these benefits. Can we fix this? Well, there's a few things that we can do on top of the system we already have. We can do things like take our applications and say, well, if the RPC doesn't work the first time, try again. And then if it doesn't work after that, maybe wait a little bit longer and try again, or add some jitter and try randomly over time. We can add entry and exit traces to say this thing started and this thing finished, which is, to me, sounds like print debugging. And we can add the infrastructure to secure these connections with authentication, which means we have to teach all our applications how to be aware, how to do TLS encrypted communications, and then we have to take on the burden of maintaining that with all of these separate teams in all of these separate languages, with the constant drumbeat of problems you have in SSL libraries in the back of your mind. Maintaining consistency like this and doing it across platforms is a thankless task. But what if we could make the space between the applications intelligent and handle all of this for us? We could get something which is language agnostic, and we also want something where we can change the configuration at runtime, not have to recompile or restart our applications to reconfigure. This is the service mesh. And the service mesh I'm here to tell you about is Istio. Istio is a complete framework for connecting, securing, managing, and monitoring a microservices architecture. Istio is built today to run on top of Kubernetes, and as you'll see, it's expanding to run further than that. But Istio does not deploy software for you. It does not care about the process of getting it onto the machines. We've invented a great abstraction for this with containers, with Kubernetes. In this case here, we may see 3 different slices of machines. The instances that make up our microservices are spread across them, but we have a way to group them together. We have the mechanisms which Kubernetes provides, so labels in this case. We can just target all of the things that have the name of web and say that particular group, which might have auto-scaling attached to it or might have other deployment methodologies, will contain our web service. So we don't need to think again about the slices of the machinery, we just think horizontally. This might be what we look like from a diagram perspective. We have a user on the left-hand side. Their traffic comes in and hits our front-end microservice. We may have something which does some processing of pictures that they upload, and we might want to scale that, again, with larger instances or based on the number of people who are using them. There may be a cost to doing this, so we have a separate payments microservice. And that payment service has to call out to an external API, which is outside of our cluster in order to take payment from the user. And then to handle users logging in, we have an authentication microservice, and that has its state stored, again, outside our cluster in a Cloud SQL database. What Istio does is enhances Kubernetes. So you install it using an alpha feature in Kubernetes called an initializer, so that when you deploy software to Kubernetes, it notices, I'm being asked to do something here, I'm being asked to change this, and add a sidecar, add another container inside each Kubernetes pod that's being deployed, which will handle the intelligence and the routing for us, again, without having to actually change your application, or even have it aware that it is being changed. So this is what it looks like with Istio. We have the sidecars which provide an ingress and egress proxy to all traffic for a particular service. So we can offload all of the functions we've talked about. We don't need to teach our application how to do telemetry or tracing or TLS. We can add other things like circuit breakers, rate limiting, canary releasing, all so on, inside our application. The traffic now does not flow directly to the services. It flows through these proxy server sidecars. You see here that all of the connection is done. Because a Kubernetes pod has everything on the same IP address, we can intercept the traffic that would have gone to that front-end service and go through our rules engine of our proxy server before handing good traffic off to it, and so on. The sidecar proxy that is used by Istio is called Envoy. Envoy is actually older than Istio. It was developed at Lyft. It's been running in production there for over a year to run all of their microservices infrastructure. We picked Envoy for the Istio project in collaboration with the community. So Google, IBM, and Lyft are the three people who have been working on Istio so far, and a number of other companies have joined since. But Envoy is modern C++ code. It's all written to the C++ 11 standard. It's been in production, again, for over 18 months before it was open sourced, and that was about a year ago it was made available. It is low memory, so it doesn't take a lot of resource when you attach it to your services, so it's sensible to deploy it in this fashion. And they had a great team who were very willing to work with us to take ideas, to build in the things that we needed to be able to enhance the way that Istio works. Here are a few of the things that it does. So it's a proxy server for HTTP, including HTTP2, and protocols that build on top of it, like gRPC. It can also proxy other protocols at the binary level. It is aware of your zone infrastructure, so you can do zone-aware failing in cases where you have an availability zone offline. It can handle a lot of the network connection things that you want, so retry budgets and timeouts, so you can say how many times I'm willing to retry connecting to that server before giving up and telling my service that it just didn't work. You don't have to worry about reloading, restarting the application to add configuration to it. You just connect to it with an API, very similar to Kubernetes, and then you're able to change its configuration at runtime. Now, the Istio team, primarily driven here by Google, have made a lot of contributions to the upstream Envoy platform that were needed by Istio. So, for example, fault injection, being able to say, have a certain number of requests on this particular thing fail so I can see how my application behaves in that case. And traffic routing and splitting facilities to be able to handle the cases where we do these canary deployments and we want to do certain percentages, which we'll see in a second. So this is the architecture of the Istio system. So we'll take just two of the microservices we saw before. Ultimately, this is very similar to a software-defined network. So the sidecars, the Envoy proxy servers that we deploy alongside the applications, they carry the traffic. So again, they transparently intercept it using IP tables in the pod namespace. At the bottom here, we have the control plane, which takes care of configuring and managing the data plane, but it doesn't handle the traffic itself. We have three components. We have the pilot, which does the configuration. So again, it looks at the rules that you configure with the API to the Istio control plane, and then updates the envoys so that it behaves how it needs to. It handles service discovery within the clusters as well. Istio auth at this end handles a certificate authority and giving TLS certificates to the proxy servers so that we can do things like say we now have a connection between these two servers where we've authenticated that both ends are who they say they are and they're allowed to connect to each other. And again, the applications don't even need to have SSL involved. They can just speak HTTP and the proxies will handle all of that for you. The mixer in the middle is one of the more interesting pieces. It handles on every request the checks that are required to make sure that you're meeting the policy, and then it also sends telemetry information so that, again, without doing any changes to our application, we can get visibility and observability inside our cluster. So let's talk about those 5 things that we get from Istio in detail. First of all, we'll cover traffic control. Here we can decouple the control of traffic from infrastructure scaling. So previously we might do something like say we're going to deploy 20 instances of an application and 19 of them will be the old version and 1 will be the new version. So by definition 5% of traffic is now going to a new version. With Istio we can deploy whatever number we like and we can say whatever percentage we like gets sent to these new versions. So here's a simple traffic splitting rule. So for all traffic from the front-end service, that's destined to the pictures service, we'll say we want 99% of that traffic to go to the thing which has the version 1.5 label and the environment prod label. And we can say 1% of the traffic goes to the 2.0 alpha that we've deployed. So it doesn't matter how many replicas we have. In this case, it might just be 3, but we balance them still with 99% of the traffic going to our existing environment, and then 1% on the right. That can all be programmed on the fly with these rules. Envoy will periodically be updated as you update your configuration, and there's no disruption to your service. Here's another example we call traffic steering. So because we're operating at layer 7, we can look inside the packets, and in this case we can look at the user agent, which again a layer 3 network has no idea about. But in this case we might say any traffic from an iPhone is subject to this rule, where we're going to direct a certain proportion of the traffic to a new version that we want to test because we want to test for a certain device. As an internal service, a caller can actually say, I know I want this particular version. So again, you could say, I'm v2 of this service here, now I'd rather talk to the v2 backend I've deployed. It's another case for traffic steering. Visibility. So once you have some view inside your cluster, you can respond to the things that it's done. So we want to think, well, why is Istio different to monitoring systems we've looked at so far? We don't think that monitoring and tracing should be an afterthought that you just add on to your infrastructure once you've built it. We want to be able to have a holistic view of an entire fleet of applications. We don't need to worry about a development process to do instrumentation for metrics. Metrics aren't special. Every component should be able to emit them. A lot of people think, all right, well, I'll just do log scraping afterwards. Well, ultimately, we want this sort of consistency where we can also get portability, where we take in these metrics and then we can send them out to whatever monitoring logging service we're using. This is the Istio dashboard. So this is Grafana backed by Prometheus. It's available just by deploying a service inside your cluster. And for some of the services deployed in the example here, you can see, for example, an overview of the status of the number of queries per second, requests per second to the whole cluster. But we can do more interesting things like say, what percentage of applications are giving 500 errors, which implies a failure? Or what are the P50s and P90s and P99s of response time? Again, aggregated across all of the instances of calling and responding services inside your cluster. This is what you get when you install the book info sample application. And you don't have to configure any of this. It is aware, it's backed by Prometheus, which knows which services are available in your cluster. And the Istio mixer is able to send metrics out to Prometheus out of the box. If you want to do investigation, so the Zipkin Open Tracing is another provider which is provided by the Istio mixer. All of the calls which are made are routed through the mixer, and then trace IDs are sent, which can be sent to Zipkin. So you can dig in and see for all of the different calls that are in a chain of microservices that make up a response to a user. We can do things like figure out which ones take time, and again, aggregate this over the cross of all of the responses we have, not just any particular 2 instances that we're looking at. Let's have a look at how that works. When you make a call to a particular service, the proxy sends information about that call off to the mixer. It will say things like how long it took to serve that particular request, what the status code was, and the source and destination IP. So now the mixer has that information, and it will normalize that and send it to whatever backends you have configured. So for metrics, for example, we have Prometheus and InfluxDB adapters, but you can also write a custom adapter. So you can just take the code, take the input there and output it in whatever format any other application you use for metrics is concerned. And you don't have to worry about changing any of the infrastructure when you want to add a new metrics backend. Tracing is similar. We don't have to worry at the application level about generating tracing spans. The applications just send a little bit of header information, which is provided there by Envoy. The mixer takes that and it sends that off to a tracing backend. So again, Zipkin, the open source distributed tracing, Google's stack driver tracing, or any other custom backend that you'd like. Now let's talk about resiliency and efficiency. So in our experience with working with a diverse set of customers, we find that 95% of them are happy with the out-of-process sidecar implementing the resilience features. So circuit breakers here are a pattern. We say, we're going to look here for an example for 7 errors in a row. If an error is detected, we will shut that circuit down for 5 minutes, so that traffic will travel over a different path, and we'll just keep detecting that over time. And again, these are things that you configure in your cluster at runtime. Some of the features here, so timeouts between service calls, retries, health checks, load balancing with availability zone awareness, and as I mentioned before, fault injection, so being able to say, I'm introducing some faults into this connection to see what happens, which we'll look at over here. So in this particular example, we might say that between service A and service B, we say we're going to wait 100 milliseconds for that service, the movie service here, to respond. And we'll retry 3 times if we don't get a result. So we've effectively said, all right, it's going to wait there 300 milliseconds before it returns to the user and says, no, I can't give you that particular piece of information. And then our front end should fail gracefully in that case. But here, our movie service needs to talk to its ratings for number of stars, and it has a 200 millisecond timeout it's willing to wait, and it's only willing to retry 2 times. So a call to this movie service could cause you to wait 400 milliseconds in the case that the rating stars service is offline, but you're never going to find that out because you've got a 300 millisecond wait on the first one. So injecting delay and testing what happens in these cases is a great way of finding in your microservices architecture things that will fail that you were not aware of at the time that you built it. So Netflix, for example, when their personalization recommendation system is down, they just fall back to generic ones. It's great when it's temporary, but if you don't know that it's not going to be temporary, then you might have built yourself a feature that you find your users never actually see. Now, from the efficiency perspective, the Kubernetes load balancer itself is only layer 4, and we've invented the ingress construct to do layer 7 load balancing. So the Istio ingress is implemented as a layer 7 load balancer. Handles all of the things you'd expect it to do in terms of being able to do affinity between services. Again, not just from an IP level, but for things that may end up running multiple on the same box. We do the TLS offloading. So we use the boring SSL implementation in Envoy, which came about as a response to the OpenSSL challenges that we had a couple of years ago. So we have a modern, well-maintained SSL stack that was been pared back to have just the things that it needs. And you don't have to worry again about, in the event of an SSL vulnerability in your application, having to go through and find a version that works for whichever particular platform or library you're using. You're able to offload all that into one place, which you can update if you need to in the event of problem. And then that will handle conversions, for example. If you have backend, you want your service to come in over gRPC, but your backend only speaks HTTP, you can do that conversion and vice versa. Security, similarly. So Istio wants you to be able to validate that connections between services come from identities secured that they're expected to. And an identity may be more or less granular than processes and jobs and workloads and so on. But we need to trust that the person at the other end is the person that they say they are in both directions. And we want to do that so that people can't spoof this just with DNS names or IP addresses or so on. So out of the box, we want security. How do we do that? So the Istio auth service has 2 things. So first of all, the team of people who worked both in Google and outside are working on an open source identity service, which is called SPIFFE, or the Secure Production Infrastructure for Everybody. So if we talk about the traffic flow here, we have the Istio certificate authority. It will give certificates for the service accounts with the names as defined by the standard for the applications that we run inside our cluster. These certificates adhere to the SPIFFE specification. They're distributed to the Envoy sidecars using the Kubernetes secrets mechanism. So they are each able to get access to their certificate, which is written to tempfs and is not written to the disk of the nodes. Now, Envoy uses keys to enable mutual TLS without the applications being aware. The identities are propagated to the backend applications, so the backend applications get information about who they are, and so you can enforce policies based on those identities. Istio handles certificate rotation, certificate revocation, and secure naming, so that you don't have to worry about certificates expiring and so on. You can have that as an operations task. As a developer, you don't worry about it. And we prevent DNS spoofing attacks because we're actually including information in our certificate name there about the service account that's running that application. This will respond to autoscaling. So in the event that you autoscale your application, you'll get a new instance which gets a new certificate. You don't need to worry about manual intervention. And if you want, you no longer have to worry about firewalls. So a lot of people will use network policy in Kubernetes to implement layer 3 firewalls between pods. You can keep that for defense and depth if you want, but you can also say, I have a completely flat network and I trust the endpoints. So if you think about the Beyond Corp papers that we've published, we talk about the fact that my laptop here can get exactly the same access on the public network I have as it can in the Google Corp environment, because we're trusting the identities that are issued to the machine, and we're routing through secure proxies in a very similar way to this. So the next things we're doing is we're integrating certificate management and storage systems like HashiCorp's Vault, and interfacing with HSMs is provided by cloud vendors. Finally, we'll talk about policy enforcement. So the mixer is the point of integration with the infrastructure backends. You can extend the mesh from what you had to start with to build into your existing infrastructure. Now we can say services can easily move around within the mesh, which might be deployed in more than one environment, so across clouds or cloud and on-premise. It's designed so operators can control the behavior of the mesh. Calls that are made from the Envoy proxy will do a check to say, for example, are they allowed to do this particular call? We can put preconditions in to say, well, only in certain cases. And we can also do things like rate limiting. So we can allow a user to say, you may make this call at 1 request per second, but no quicker. Or as an operator, you could say, there is a service which I call has 20 free requests per day. Users can make 20 requests, but after that, they're stopped because I don't have a plan which would automatically start charging me money. Your preconditions can include things like, is my server authenticated? Is it on a whitelist? Does it pass its ACL checks? Quota management can be used to provide fairness between different people to say, oh, we want to make sure everyone who's consuming the service is limited to about the same rate. And then finally, the mixer takes your responses, positive or negative, and sends them out, as we saw before, to do telemetry. And that enables the service producers and the consumers both to look at that telemetry through whichever service you have configured to do so. So that's the slide we saw earlier, which is talking about the Istio environment, summing up all of those things. Ultimately, we want you to think about it at this level. You again just deploy the application that you would have previously, and you don't worry about any of that. You might define some policies, you might define some routing rules, but as a developer or someone who's building an application, you build for the clusters that you were previously used to, and then you get an application that works the way you expect. To get started to running Istio, Istio supports previous versions of Kubernetes, but the new initializer feature is in 1.7 or above. It's an alpha in Kubernetes, so what I recommend you do is use an alpha cluster on Google Container Engine. So we have clusters that you can enable that last only for 30 days, but allow you to use pre-production features in them. If you enable an alpha cluster, you get access to the initializers, which means you can deploy Kubernetes objects and Istio will automatically install onto them. If you're running a production cluster, you have to actually do a bit of munging at the command line where you use the Istio control command line to add that information before you send it in. The quick start on the Istio.io web page, which we shall have a look at in a moment, is great in terms of being able to see a simple application and how it's deployed. And you can also deploy using Helm if you're interested. So I think we're going to have time to go and have a look at a little demo. All right, so first of all, Istio, again, it's open source. It's on GitHub. We've just released version 0.2. So 0.1 will let you manage objects within a single Kubernetes namespace. With 0.2, we now support Istio running in its own namespace in the Kubernetes cluster, and you can manage things that run in any namespace on that cluster. Further, we've added access to be able to manage services that run on VMs. As long as your VM is able to talk to the Istio control plane, you can have an Envoy sidecar deployed on that VM, and you can secure services that run on that. Ultimately, Istio will support other platforms like Mesos and Cloud Foundry and Nomad. It is the goal of this platform to make it possible to build a mesh which summarizes all of the things you might want to talk to. So ultimately, you shouldn't need to worry about whether the endpoint you're connecting to is something you run yourself, whether a provider runs for you like BigQuery, or a service that's running on another place. We didn't want to build these features into Kubernetes itself because we want to make this broader than Kubernetes. You might have an environment that's built up of more things. So the mesh exists outside of this, but the control plane runs on top of a Kubernetes cluster. The quick start instructions here talk about how easy it is to get started. I have a cluster running already, which is running Google Container Engine on 1.8 with the alpha features enabled. And installing Istio is one command. So you deploy a YAML file which deploys all of the role-based access control rules, all of the services, the control plane services, and all of the configuration maps and secrets required to connect those things together, a single command. Server. There we go. So here you can see the default services that we've installed here, the Istio ingress and egress, and the mixer and pilot. And then I've also got some additional add-on services which it talks through in the examples, so Grafana, Prometheus, and Zipkin. So the next thing that I've done now that I actually have Istio installed is I've just deployed a simple Kubernetes service. So here you can see the YAML. Let's just talk through some of this. So all we have here is the description for a Kubernetes service. So we have a few different microservices. We have a few different versions of it. We have basically a little bookshop that we'll show you in a second. It lets you see ratings of books, lets you submit and receive book reviews. And again, some of them we have a couple of different versions of that, which you can see if you go through the examples we've created for you. We also, again, have our Istio ingress, so we're able to take incoming traffic. And we have a rule here that says for our product page service, talk to the backend, which is product page. And that's a microservice running in our environment. So if I go back to the service, you see here the IP address of our Istio ingress, which was, sorry, in this window. That one there. And if we go to /product page, we see our simple bookstore application. So the first thing to note is that we have a rule which is talking about traffic between 3 different versions of the review rating service. So here we have one that shows red stars, one that shows black stars, and one that shows no stars at all. And what I'm doing is I'm just hitting reload, and you'll see that the configuration in the default here is splitting traffic equally between these 3 services. Some of the examples that you will see in the book info, which I don't think we'll have time to look at now, will let you configure the relative weightings between that and what to do in the case where we're calling the review service and the rating service doesn't return in time, as we talked about. So having generated a little bit of traffic to that, we're able to do things like go to our Grafana page. So here we're seeing the success. I'm not hitting it very hard, so we're getting 100% success on that, and not very fast. So you can see, again, as I hit reload on the page, generate a bit of traffic there, generating backend traffic to all of our services. And again, you can see not just individual versions, but you can see the response times for the 3 different versions of the backends I have deployed. And because that's backed by Prometheus, you're able to do things like get graphs here of the request count over time. You can just see the latency creep up just a little bit as I've started to hit those applications. Again, if we refresh our Zipkin, and we'll say traffic in the last couple of minutes. Here we can see the traces that are running through our application. In this particular example, we are calling our product page service. The first thing it does is it goes and hits the mixer to do a check to see that we are indeed allowed to hit this service. We're then getting back details, which is the review of the book, the details of the book. And then it's doing another check to see are we have permission to hit the review service. These are all cached, and you can set a period of time that you want on that so that we're not needing to continually delay, but we say it's about 1.6 milliseconds on that one. We hit our review service, again do a mixture, and then to our ratings. And you can see actually calls here to the services as you come back and forth and how many connections they've made out to the mixer. In the event of you having, like for example, one of the things we can step through is one of the 3 versions of the stars service takes a lot longer to see, and you'd be able to see that in the aggregate using Zipkin. Okay, so there's an introduction to Istio. I'd like to thank you all very much for coming along. I now have about 15 minutes if anyone wants to ask questions. There is a microphone, so please raise your hand. We do have a little bit of time. I'd love to answer any questions about Istio or indeed where we're going with Kubernetes I can talk to as well.
Thanks a lot for the presentation.
Thank you.
I have a couple of questions. First of all, the Envoy, the proxy you were talking about that provides a great deal of functionality for Istio framework. I'm wondering where does it reside? Is it located in the same container that the application does, or another container?
Yeah, so when you deploy an application to Kubernetes, you'll normally see, you'll deploy one container inside a pod. And normally you'll see there 1 of 1. In this case, what the initializer does in Kubernetes is says, I'm taking a YAML file which says get a pod spec with this container and deploy it. And the Istio initializer says, I'm going to add a second container. I'm going to add the Envoy container, put that inside the same YAML file, and then deploy it. And if I were to, there is an outside chance I'll get the, okay, so this is the YAML for the container, for the pod, sorry, that's running our product page service, as you see from inside Kubernetes. So what you will have said to start with is you will have said a spec here which says something like this, is that this is my container, here is the source of it, here's the port I want it to run on, here's how it behaves. The initializer that runs in the cluster says, all right, I now need to add another container. So here's some arguments here. I have proxy sidecar, so it's actually going to take my Envoy container, it's going to deploy it. It says the Zipkin service is configured, so it provides all the configuration from the environment into this. So my pod now consists of 2 containers. So it includes the Istio proxy container here. You see its container name. And both of those containers are in the same pod, which means they are scheduled together on the same machine. They run on the same IP address. And then we're basically saying, transparently, take any traffic that was due to the ports that are exposed by the first container and route it to the second container. So we said for the product page, it was port 9080 or something. Traffic that would have hit that is now being intercepted by Envoy, comes in through this container, and now you can only connect to port 9080 from localhost. So you're only able to do that from the Envoy container. You're not able to do that externally.
Okay. And the other question is, does this proxy have any test support? Let me give you an example. For example, I want to run an end-to-end test. And besides, I do want to make some assertions on the several points in the middle. So probably it's a good idea to gather them, the data, the test data from the proxies.
Yes, so again, not an area I'm too familiar with, but I know that we have end-to-end tests that cover the deployment of services that run with Istio as well as the product itself. So I'd say that you'll be able to dig into the GitHub repository and have a look at some of the samples there. And there's some test samples as well, which hopefully will answer the questions end-to-end for the... Like Istio deployment is just, again, a Kubernetes service that runs. So you're able to take those patterns and apply them to your own application.
Okay, thanks.
Just a few rows back there, there's a gentleman who had a question.
Thank you for your talk.
Thank you.
I want to believe in this Istio. I mean, it does provide a lot of good features, but it does provide a lot of abstract layers, additional abstract layers. And if I don't know how it works, I don't know how to debug and how to investigate problems.
Yes.
So how reliable is it? Or do you believe in it? I mean, is it production ready?
Good question. So we don't call it production ready yet for the reason that if we come back to the architecture here. So Envoy is production ready. It has been used again in production 18 months by Lyft, been open sourced, and again another year or so after that. The components down here, so the pilot and the mixer and the new components for Istio, I mentioned before we're at 0.2 at the moment. We're going to release a 0.3, hopefully by the end of the year. That's about the time frame that we're looking at. At that point, we're going to say that we believe it's production ready for the use cases that it supports today. So again, running inside a single Kubernetes cluster. Afterwards, so over the course of the next year, we're going to move on to a 1.0 release. We will basically, as we add more functionality, we will be supporting more platforms. So we might say it's production ready for Kubernetes now, production ready for Kubernetes and VMs, and then another release maybe for Mesos and so on, until we get to the full feature set that we want for 1.0. In saying that, the Envoy part is production ready, and that is where the data plane is. So you can configure things like if you don't have any condition checking or you don't need the monitoring and metrics, you could just turn the control plane off and all the envoys will keep working. And so from that perspective, we are seeing people that are running this, again, don't do what they are doing, but they're running in production today. They're getting some of these benefits. We think that as we've done more testing and validation, so please start using it in beta. So when we think things are ready for production, it's because we've said we've seen people use this at scale and become comfortable with it. Okay, in the corner over there is two of them.
Thank you for your talk. Well, I have a bit question, kind of off topic, but will Envoy or Istio support any way binary protocols like protobuf or Drift or so on, and how you work with it in Kubernetes?
Yes, so I believe that as of the release we just did of 0.2, that we now support TCP proxying. So you can take any binary protocol and that. Again, Kubernetes doesn't really care. You just say expose a thing on a port. And again, from the Istio perspective, you probably just say forward a thing on a port. I believe it works transparently. I haven't tried it myself yet, but I did see it in the release notes. It's about 1 week now since that's come out. So.
I'd like to ask a question about Istio, and is it really viable outside Kubernetes?
Is it viable outside Kubernetes? The goal is for it to be viable, yes. There is support for running it with Docker and Consul today as part of the example code. We've decided, at least for the beginning, that because all of the components required to run the control plane duplicate things that are in Kubernetes, we don't want Istio to be its own thing that you deploy just on bare metal when we have those components that provide Kubernetes today. You could use the Kubernetes control plane. Sorry, you could put the Istio control plane on Kubernetes and have it manage services that are running somewhere completely different. You could just say this is the box that runs Istio and then manage the services. The things that it supports today are single VMs or instances of VMs that are outside. Over time, we want it to support multiple Kubernetes clusters or combinations of Kubernetes and other clustering environments and other platforms as a service and cloud environments, for example. We're working to a standard identity specification. So once we, as an open community, have settled on that, we'll be able to do things like, say, use this token to deploy BigQuery or Dataflow or any other service just provided from the cloud. So it's, over time, not going to be coupled to Kubernetes, but it needs it at least now for the control plane. And we're talking about what we'll do with whether we'll keep it coupled to Kubernetes for the control plane. We're looking at that actively in the community at the moment.
Thank you. That covers it.
All right, so just behind gentleman there, we have probably got time for one or two more questions.
My question is it possible to implement some custom logic, for example, using program language to not just check regex, but implement some language check?
Yes.
Rule?
Yeah, so the mixer basically takes the rules that are specified and then turns them into... so your Envoy will go out and call the mixer. You could implement a backend of your choice there. So you could implement your own check for whatever particular reason. So not just checking, you could take that and then call off to a completely different service. That is why we have the mixer service, so that you don't need to do that in each Envoy, that you call out to what will probably eventually be a cluster of mixers if you run a larger service, and then you're able to extend them with your own code. So you're able to say, this is how I need to do a check for my particular environment.
Good. Thank you.
Okay, if we have no more questions, I'll be out in the discussion area for the break, and thank you all very much for your time.